I have 4.4 times 10 to the negative fourth is going to equal x squared 0.175 minus x. All right, let's do a quick double check. Can we use x is small here? 0.175 divided by 4.4, 10 to the negative fourth. It is greater than 100. Yes, we can use x is small. That's helpful. All right, so let's take 4.4, 10 to the negative 4 times 0.175. And so that's 7.7 times 10 to the negative 5. Let's take the square root. So here we get x equals, we can say 0.00877, roundabout. All right, and that equals our concentration of OH minus, because this is a base. The question asks for pH, so most of us like to do the pOH, so that's going to be our negative log, 0.00877. So let's do that. Negative log of the answer there, 2.06. 2.06, so that means the pH, 14 minus 2.06. So 14 minus that answer, 11.94. All right, so that's the first part. Next, this is just a standard titration using stoichiometry. What volume is added at the equivalence point? Equivalence point means moles of acid equals moles of base, so everything is completely neutralized. So here we have, we need to write our equation for our acid and our base. So CH3 NH2 plus HBr is going to equal, what is this going to make? CH3NH2 plus and Br minus. That's what it is. Oh, not an equals, arrow. All right, so when you balance the equation, it's all 1-to-1 ratio, so that makes it easy. Did you need to write the equation? Probably not, but you can if you want to. All right, now, I do this factor label stoichiometry. So let's start with what we have both the volume and the molarity of. So we have 25 milliliters of CH3NH2. And I know I have 0.175 moles CH3NH2 over 1,000 milliliters. Losing my train of thought here. In the equation, 1 mole CH3NH2 is equivalent to 1 mole of HBr. So that's how much it takes to neutralize it. And then the HBr that we're working with is 0.150 moles per 1,000 milliliters. Thousands cancel out. So let's take 25 times 0.175 and let's divide that by 0.15. So 29.2 will work. 29.2. That's how I did it. Yes, Drew, do you have a question? I am recording this. It will be on my YouTube channel, so don't worry if you don't see it. All right, now, what is the pH at 50% neutralization? That means the same thing as half equivalence. Where does the other H go? It makes water. All right. All you really need here is your mole ratio. All right. So, what do we know when we are at half equivalence? There's a shorthand way. When you are at half equivalence, what is it? pH equals what? Who remembers? pKa. Yes, pH equals pKa. All right. So it's only sort of a shortcut in this problem because we have a Kb. But we're going to need Ka so we can use our Henderson-Hasselbalch equation later on. So right now we have Kb. So we know that Ka times Kb equals Kw. All right, so Kw, 1 times 10 to the negative 14th. Kb, 4.4, 10 to the negative 4th. Ka times that. So let's divide 1, 10 to the negative 14th, divided by 4.4, 10 to the negative 4th. So it's a small number, 2.27 times 10 to the negative 11th. So Ka, 2.27 times 10 to the negative 11th. Again, most of this you can probably just do on your calculator. And now to do pKa, negative log of 2.27, 10 to the minus 11. Now, the good news is here, with a number that's this small, we know that x is always going to be small here. Negative log, so pH 10.64. Or somewhere around there, depending on how you round. All right. Next, what's the pH at the equivalence point? All right. Here, we need we know how many milliliters is going to take. Make sure I say this right. So we know moles of acid equals moles of base. Make sure I do this right. Let's react this with water. CH3, NH2. This is going to be a shorthand form of our equation. So here, I'm just using the positive hydrogen ion instead of the hydrobromic acid. So I'm just taking that off. That's going to leave us, this plus is going to go here. So we're going to have CH3, NH3 plus, and leaves us with water. Now, what we got to figure out next we know that all of so moles of acid equals moles of base. So it doesn't matter which one you do here, so we know how many millimoles. Again, making sure I tell you this the right way. 25 times 0.175. So here, we know these are neutralized, so you can say that all of the base, because we're doing a base here, is now the conjugate acid. Here's the conjugate acid. There's your base. All right, so when I did 25 milliliters times 4.375, no, that was my answer. 0.175 molar, we get 4.375 millimoles. So that's how much we have here. All of our acid is conjugate base. So 4.375 millimoles. Now we need our total volume here. How do we know to use that equation? Oh, it's just a shorthand one. You can use the other one if you want to. It's easier for me to do base and acid. I don't like titrating bases with acids. I'm pretty sure I'm only going to ask you to do, at least I'm going to. I don't know what the, I haven't looked at what the ACS is going to do. But it's a good question. You could use a shorthand equation if you want. It'll work for balancing, but 1-to-1 ratio. So now we need our total volume. So we start out with 25 milliliters of our base, and then we need to know our 29.2 milliliters of acid from the equivalence point. So I'm going to do this in one step here on my calculator to save time, which means I have to use parentheses, right? We'll see if I do it. Plus 29.2. So that is 0.0807. All right. Now we have to write this dissociation equation and go back the other way. So when you take this, we're just writing the equation backwards now. So CH3 NH3 plus, because it's going to go, so this is the left-hand direction. So if you can keep track of this, you do not have to write the equations again. When we put this acid in water, we're going to get our original base, CH3 NH2, and our hydrogen ion concentration. Or if you just want to write H+, that's fine. If you don't want to put water, then don't. So here, now we need an ice table. 0.0807 minus X plus X plus X. 0.0807 X and X. All right, so now this here, this is the conjugate acid. So make sure when you use this, you need to use Ka, which you've already calculated up here. So be careful with that. Make sure you use Ka. If you're doing this titration the other way, where you're titrating a weak acid with a base, you have to use Kb. So when you do these, maybe it will be easier for you initially to just figure out Ka and Kb. Where did the 29.2 come from? It came from part B, volume of HBr at equivalence. 25 milliliters is what we started out with. All right, so we have Ka, which is 2.27 times 10 to the negative 11th. X squared, 0.0807 minus X. X is small, we don't need it. So we'll multiply that by 2.27, 10 to the minus 11. This is a very small number. Take the square root. So X equals 1.35, 10 to the minus 6, which is our hydrogen ion concentration. So when we do pH, we need the negative log of that, 1.35, 10 to the minus 6. Negative log of the answer, 5.87, somewhere around there. So notice it is on the acidic side. It should be, because we are adding acid. So at equivalence, when you're doing a weak base with a strong acid, you should have an acidic pH. All right, now for one of our millimole calculations here. If we add 5 milliliters of the hydrobromic acid. So here, this is before equivalence. So let's see how much of each we have at this point. So we have, I'm going to do my millimoles first. So of our, here, CH3, NH2, and H plus, making CH3, NH3 plus. Or if you want to write water. I just keep making this equation shorter and shorter. It's because I'm tired of writing it. Alright, so here we have 25 times 0.175, so that's our milliliters, that's our molarity, which gives us the 4.375 millimoles. So we'll put that here, because remember we have to do our stoichiometry calculation first before we can do our equilibrium calculation. That's what happened here. We had to do our stoichiometry, then we had to do equilibrium. We cannot use Henderson-Hasselbalch at equivalence because it is not a buffer system. You have no base and all conjugate acid, so you can't use Henderson-Hasselbalch at an equivalence point. All right, so now how much HBr do we have? We have 5 milliliters times 0.150 for the, move that over where you can see it, molarity, 5 times 0.15, 0.75. So here we have 0.75 millimoles. Now, at this point, all of our acid is going to go to our base here, minus 0.75, which means that much is going to get added as a conjugate base, because base becomes conjugate acid. All right, so we have 4.375 minus that, 3.625. 3.625, 0.75. All right, now do a quick ratio here, and does it fall between 0.1 and 10? Yes. Here, 3.625 divided by 0.75. There we go. It is between 0.1 and 10, so we can use Henderson-Hasselbalch. That makes things a lot easier. pH, pKa plus log, base over acid. Always remember base over acid. Now here, make sure you know which one is the base and which one is the acid. All right, so we already figured out pKa up in part C. If you don't remember that, calculate it again. That's okay. I'm just going to plug it in. Plus the log. The base in this case is what we're titrating initially. 3.625, 0.75 of acid. So here we have more base than we have acid. So our pH should go up at this point. So let's take the log of that and let's add it to 10.64. 11.32. Fun calculations. All right, I think Trey wanted me to do number 4.